Differential equations, we're in section 1.3, and this is a very different section in the chapter. We're really not solving differential equations or even naming intervals and so forth. What we're actually doing is just setting up math models in a differential equation format. Real-world situations modeled by differential equations. And we're just going to quickly go through them. Assume that population growth is proportional. And notice this symbol right here. It looks so much like the alpha, Greek letter alpha. This symbol for proportional is something that our textbook will use. And just wanted to point that up. And make sure that you were aware of that. So what we have is population is going to be changing, being proportional to the population at any time. And what you're going to see is dp dt then is some number, constant, multiplied to the population. What we saw in previous classes, like in Calc BC, it's P is equal to P naught e to the KT. This winds up being an exponential curve, a very famous one that you've seen in Algebra 2. We also have the logistics curve, where M is the maximum carrying capacity, or also known as the maximum population. That, of course, is where we assume that our population does not grow without bound. Newton's law of cooling and heating. We have the temperature changing with respect to time. It's proportional to the difference, the subtraction of the temperature and the surrounding medium, the room temperature in this case. So, we've seen that before too. Spread of disease. Wow, this time of year too with flu season. This can be very interesting. A differential equation can represent the growth of the flu or the spread of a disease. Let's just get our definitions. X is the number of people infected. Y is the number of people not infected. What we're seeing is how the number of people affected are changing with respect to time, the growth of that disease, so to speak. It's proportional to the product of the number of people who are infected and the number of people who are not. Mixtures. Wow, we're going to have more later, and we'll really jump into this. But as you are mixing in, say a salt solution into a tank of water and so forth, we're really going to get into that. A differential equation can see that. We'll deal with a full-blown example. Let's get into some physics though right here. Newton's second law of motion. Wow, one of the most famous formulas that you're going to see. F equals ma, right? So Newton's second law of motion. Let's assume that only gravity, and you would be told this as well, that only gravity acts on an object. If that's the case, what you're going to see is this. Using Newton's second law, you could say, well, the force that is applied here would be ma, but, your a there is going to be acceleration due to gravity, and this is where downward is going to be assumed to have negative values. Downward is negative. That's not always the case, by the way. You have to have that agreement when you're looking at this. Well, what you're going to see immediately is that your m's would divide out. And what is a? Well, a, your acceleration, you might know it's your second derivative of position. And this is how this could be derived. Now, as we look at this second one, let's just assume that they tell you that downward directions are positive. You can think, oh my goodness. Well, yeah, you're free to, give that designation either way. So we can say, well, look, gravity is pulling down. Instead of saying m times negative g, we could say m times g. But let's just say that we also have air resistance. If we had air resistance, they might tell you in the problem, is proportional to velocity. Now, if that were the case, downward is positive. That means upward is going to have a negative connotation here. We'd have negative kV. So what are we seeing? We're seeing this. We could go back over here to this work and say, look, we could have MA, but A is really dV dt. And what is this force? Well, we have this positive component, that's mg, and then we have this negative going upward. Then that would be a minus kV. That's the air resistance component. So we've got the force of gravity, we've got the force of air resistance, and there you have it. You could have Newton's second law of motion. Well, from here, we're really going to pause and slow down just a little bit to talk about electrical circuits. Electrical circuits, my goodness, I think sometimes kids panic a little bit when they see this. And we're just going to break it down and talk about it. Now, again, you're not solving an electrical circuit differential equation. We're just going to set it up. So in an electrical circuit, you could have inductance. You could have L right here. And, of course, L in a circuit would look like a coil in general. So you'd see a little coil. Most inductors look like that. But inductance is really going to work in this regard. It's a property where an electromotive force is generated, or a voltage drop will occur. It's another way of saying that. If there's a change in current, you can think of current as if it was water flowing too. So if current is I, a voltage drop, and we're just going to make note of this right here, a voltage drop would be L times di dt. So that's really what we'd like to be aware of. Current is I, and di dt is the change in current. So L times di dt is a voltage drop. Okay? Capacitance, usually you're going to see capacitance written this way with two parallel bars. Capacitors are really storing an electrical charge. There's going to be a voltage drop there as well. So Q is a charge at time t. So when you divide by this capacitance, it's a constant. So L is a constant, C is a constant, R is a constant. Capacitance, you'd have Q over C. This is another voltage drop. Okay? And then finally, resistance. Well, you might have seen this very famous formula in physics, V equals I times R. That's the measure of voltage, a voltage drop given a resistor. So a resistor, you have current I times this constant R. That would measure how much your voltage would drop through this resistor. And a resistor, you almost have like a sawtooth kind of a picture in a circuit. And just getting back here, so we've got these basic formulas. Q is a charge at time t. What is current? Current, I, is how your charge changes with respect to time. So I is really dq dt. And then if I take a derivative on both sides here. We'd have the second derivative of q with respect to t. That equals di dt. So here's what you can do to get a differential equation. We're going to add up the voltage drops. So we have, for inductance, L times di dt, but di dt could also be the second derivative of q with respect to t. So that's what we've got right here. So that's your voltage drop, but we're using the variable q. And then we come to our resistance. Well, I, remember, is dq dt. So another way we could write our voltage drop here, it's dq dt times r. Well, we've got that component right here. And then we'd have q all over c. What's going on right now? You have a second derivative of q, a first derivative of q. You've got q right here with that 1 over c. Add all that up, you will have the voltage on a closed loop. That's always going to be E of t. This is a second order differential equation. Second order because we have a second derivative of q. So this is all from the perspective of a differential equation where we wanted to write everything with respect to q and its derivatives. Of course, you could also say, well, couldn't I have just gone back to the inductance, and couldn't I have just kept that as a voltage drop of L times di dt? You could. And guys, this is known as Kirchhoff's second law. Look, for your inductance, for that voltage drop, that's L times di dt. You'd say, what about your resistance? Well, now I'm just going to have I times R. And then we'd have Q all over C and set that equal to E of t. So that right there, guys, would be Kirchhoff's second law, and it would be a different type of differential equation. You can see right here, this is a first order differential equation. It's really with respect to I, the current. So we just have to get used to this. It's going to be a while before we actually solve electrical circuit problems. Today we're just going to try to get them set up. So I'm going to stop the video now because we're going to have to pick back up and deal with one more example. I said earlier that we are going to look more in depth at a mixture problem. We're going to do that in our next video.